folks, so this is my second attempt at recording this set of slides. The first attempt did not include a screen capture, so I'm recording again, and I'm gonna be a fish. So enjoy! So first I'm going to talk about some data and motivation on how we can quantify uncertainty. So here I'm looking at Elmhurst data from the Open Intro package, and we're looking at the relationship between family income and gift aid from a randomly sampled group of 50 students from Elmhurst College. So gift aid is financial aid that does not need to be paid back, as opposed to like debt aid, loans, etc. And as we can see in this plot, there seems to be a nice linear and negative relationship between amount of gift aid received and total family income. And when we use tidy models to fit this data using a linear regression, we can see that. And we can see that the average expected gift aid when family income is 0 is approximately $25,000 versus every $1,000 unit increase in family income is associated with a $43 decrease in aid, as I've produced here. I've already spelled out this interpretation, but I've got it in text for those of you who are, well, just reading the slides. So effectively, this is not a prediction, it's not a promise, it's not a guarantee, but it's describing the current state of being in this association. So we would expect students to receive a net aid difference effectively of $43 on average less for each $1,000 of family income. That's not to say an increase in family income is going to cause a $43 reduction in aid. It's not what we're saying here. We don't have any causal claims. All we're doing is telling you, well, this data and this regression is telling us that right now you can predict family income from net aid and vice versa. But is it exactly $43.10 for all the students at the school? No. We can see that from the plot and from what we've learned in our journey till this point. Inference. So inference, statistical inference broadly, is the process of using sample data to make conclusions about the underlying from the underlying population the sample came from. So we're using it to draw an inference. And so far we've done this a lot of different ways, but they've all had the same kind of blueprint. We use data from the sample to calculate our sample statistics, which are then used as the base estimate for our population parameter. The window around that is frankly a product of how confident we are in our estimate. And because I'm a fish, this is a little more ironic. But if you were to catch me, would you prefer to try and catch me with a spear or a net? Without any of the implications of what that means. Effectively, would you like to have one chance to catch me as a fish, or a lot of chances? Because that's the idea behind a confidence interval. If we want to capture the population parameter, it's much preferred to report a range of values that we might be, rather than try and guess the exact single value. Because if we report a point estimate, we're probably not going to hit it. It's infinitesimally small and unlikely. And so it's easier to report a plausible range. More than easier, it's more credible and plausible and useful to report a range of values, effectively telling us that somewhere within this range we have a good shot of capturing our parameter. And that's what a confidence interval is. It's a plausible range of values for the population parameter. So in order to construct a confidence interval, we need to quantify the variability around our sample. So for example, if we wanted to construct a confidence interval around a population slope, we would need to have a plausible range of values around our observed sample slope. This range is going to depend on how precise and accurate our sample data is as an estimate. Now, quantifying this requires a measurement of how much we expect our sample to vary across samples. How much do we expect our data to vary? Now, I've got a couple of token examples that don't really fly as well in a virtual setting. But suppose we were to split our class down the middle, all 12 of us. 6 on each side, and ask each student for their height. Then we calculate the mean for both those sides of the classroom. Would we expect the mean to be identical? No. Probably close, hopefully, or wildly different. Well, spoilers, close but not equal. Now, what if we did this a little more extreme and also put in some real numbers? So let's say I have a random sample of 50 students, and in that sample, 5 of them are left-handed. Now, what if I were to do that again? Would I expect exactly 5? Would I be surprised, though, if there were only 3? Probably not. Would I be surprised if there were 40? Yes, because that is drastically different from our first estimate. So, effectively, what I'm trying to highlight here is that we are trying to quantify the variability for any population, or any estimate of any population parameter. And we're about to start talking about how to do that via simulation and bootstraps, in contrast to the central limit theorem, which makes assumptions about our distribution and is heavily dependent on those assumptions being correct, assuming that our data are normally distributed, things like that, and that the statistic that we are estimating resembles like a t-statistic for any individual parameter, and that's a lot of assumptions. And if you know, well, word of caution, whenever you make assumptions, at least this is a Garrison family idiom, that tends to make you, I butchered the idiom. Effectively, making an assumption makes an ass out of you and me. Okay, so instead of central limit theorem, we're bootstrapping. And you may be familiar with the idiom of pulling oneself up by one's bootstraps. Effectively, this means to accomplish an impossible task without any outside help. It's based on a very entertaining childhood story, but effectively it's an impossible task, just like pulling oneself up by their bootstraps. Let's think about how that would work. In this case, our impossible task is estimating a population parameter using data only from the given sample. Just as a note here, the idea of saying something about a population parameter using only information from an observed sample is the crux of statistical inference. So let that idea marinate. So let me illustrate. So here we have one sample of students from Elmhurst College, and our estimate here is a slope of approximately -$43. Now we're going to make the assumption that there are more students like the ones in our observed sample. And here I've simulated more data of people that resembles our population. And the purple dots are the ones that we actually have, but we don't know what the true slope is. We just have one estimate. But what if we were to repeatedly sample? So if we were to take a random sample from our data with a replacement of the same sample size as our original sample, and then we calculate the statistic for that. So it can be any statistic, a mean, a median, proportion, slope, really anything can be computed this way. And then we repeat steps 1 and 2 huge number of times to create a distribution of parameters based on our data, rather than make an assumption about what that data shape is. And so that way we can actually calculate the bounds of whatever confidence interval we want by just taking the middle percentage of the bootstrap distribution, be it a 90% confidence interval, meaning that we take the middle 90% of our distribution, and so then we have 5% on either tail, 99% confidence, etc. Let me illustrate after I illustrate. So here's a first bootstrap sample. We've sliced it up from our Elmhurst data and fit that model and plotted it here. As you can see, the slope is approximately 33 bucks as opposed to 42. Now we do it again with a different slicing of our data. We have a slope of negative $52. The third time, $41, $49. And so when we plot those all together, we get a family of slopes derived from our data that should give us a better sense of the range of plausible values. Now we can do this an infinite, well, not an infinite, but pretty close to infinite number of times. So here is that same data plotted with many, many samples. Each of those gray lines is a fitted slope based on a bootstrapped permutation of our sample. Excuse me, Archie is sitting on the keyboard. Okay, so now when we plot the distribution of those bootstraps, we can see that we have a distribution of whatever our parameter is. And so if we're interested in a 90% confidence interval, we can find the 50th percentile, and that's our effectively our estimate, and look at the parameters. We have an upper bound and a lower bound. And we can now compare that to our that other estimate. So now for each additional $1,000 of family income, we expect a reduction in gift aid between 70 and 20 bucks on average. It's a wider estimate. It does capture our point estimate, and we could demonstrate that this works by simulating data from a known population that we set up, effectively run a quant study to confirm this. And I encourage you to do that on your own time if you would like. And so here's the code in order to do that. I've done this bootstraps 1,000 times. I encourage you to poke around and try it out. So that is wrapping up my second attempt at recording this video and last attempt. So I'll see you later. Bye!